So we have one final simulation here. So here we've got a 30,000 observation simulation, so the biggest one yet. And we have collect 30,000 observations of picking a card from a deck of 52 cards. So we have a standard deck of playing cards, and we are wanting to draw from that deck 30,000 times, obviously with replacement because we only have 52 cards.
Yes.
So we can now do the simulation two different ways. So we're going to do a simulation using numbers and simulation using the suit and the rank. So there's two different approaches to this. So in both times, we're doing a simulation of 30,000 results, so we know the basic simulation pattern now. So we're going to say data is equal to an empty list for I in range 30,000, colon, and then indenting after that, I want to just use numbers. So I'm going to number every single card between 1 and 52.
Okay.
So basically we could assign 1 to be the ace of spades, and then 2 could be the 2 of spades, and so forth. So every unique number has a unique card. So I'm going to say my card is equal to random.randint 1, 52. That's going to choose one of these 52 random cards. And then I need to accumulate that inside of a dictionary. So D is equal to card, inside quotes, colon card, close curly brackets. Then I need to do data.append to append my dictionary to my data list. And then finally, df is equal to pd.dataframe of data. So if we get this, I expect to see a data frame that has the column card, and it should have numbers between 1 through 52.
Yep, that's exactly what we have, 30,000 rows, and I have 19, 20, 52, 17, 45, etc.
So to me, that doesn't actually seem very useful.
Yeah, because what is 17 for a card? What does that actually mean?
So we could have this translation table. This doesn't seem very natural. And what I love to do is make it really natural for us humans. So computers do numbers great, but I want to know if I have the 3 of clubs or your favorite card, the Queen of Hearts.
Yes.
So I'm going to go ahead and rewrite the simulation, and I'm going to actually think about this card deck as a series of real-world scenarios. So when we actually draw a card, we can think about, when we draw one of these cards, we can think about drawing the suit. So we might have a pile of all the hearts. So we're going to think about what suit we want, and then we're going to think about what number we want on the suit. So I'm going to actually have two different simulations, or two different real-world variables. One variable is a suit, which has 4 different combinations, and one variable is the rank, where there's 13 different combinations. So we'll simulate both these things, store both those pieces of data, and we still have 52 possibilities. The state space is exactly the same. But we have something that's a little more friendly, that corresponds to the deck that's in front of me. So to do the simulation, it's again the same pattern we've always done. Data is equal to the square brackets. For I in range, we're doing a 30,000 simulation result. And then we're going to say my suit is equal to random.choice. And inside of that, I need a parentheses, and then I need a list of all my suits. So in here, I'm going to go ahead and write club, comma, heart, comma, diamond, comma, spade. For the 4 different suits, close my list and close my function. And then that's going to simulate which suit I get. And then I'm going to do rank is equal to random.choice. And we need to list all the possible ranks. So because we have both numbers and strings in here, because I'm thinking king is a string, it's not a number.
Yes.
So we're going to have to put strings around everything. So we're actually going to kind of break our normal rule in the sense that we want our list to all contain the same type. So what we're going to do is I'm going to start with ace and put a quote around the A for ace. And then I'm going to put quotes around the 2. And we're going to treat the number 2 as a string. Then quotes around 3, quotes around 4, quotes around 5, quotes around 6, separating them all by commas, quotes around 7, quotes around 8, quotes around 9, quotes around 10, quotes around J, quotes around Q, quotes around K. Close my square bracket, close my function. So what I have is I have every possible suit and every possible rank, and now I just need to do the final 3 steps of the simulation. We need to accumulate in dictionary. D is equal to suit in quotes, colon suit, comma rank in quotes, colon rank. So we're accumulating all of the suits and the rank information inside of our dictionary. So it's always going to be every real world variable gets accumulated inside dictionary. Then I say data.append D. And then finally, outside of the function, outside of the for loop, not having indentation, we say df is equal to pd.dataframe of data. So at this point, we have simulated a whole bunch of drawing of cards from this deck of cards. And if you type df, Carly, what do we see?
So I see 30,000 rows with the suit and the rank. The suits are diamonds, spades, clubs, and hearts. And then the ranks are 2 through 10, and then jack, king, queen, and ace.
Awesome. So this is great. We've basically just drawn from this deck of cards 30,000 times. This is phenomenal. This is something that would have taken us hours to do.
Hours.
That we did in just like 10 minutes.
Yes.
So a couple analysis questions here to finish us off. What is the estimated probability of drawing a heart? So again, I'm going to do this both ways, because especially since Carly's here to help us out with the statistics. So estimated probability of, so we have 30,000 draws. How many of them do we expect to be a heart?
So we would expect 25% to be a heart.
25%.
Since there are 4 suits, one of them is heart.
So 30,000 divided by 4 times 0.25. Can you use Python to help me out here?
Yeah, so that ends up being 7,500.
7,500 is our expected value. And then the Python is going to be really simple because we have that nice translation of suit and rank. So let's say df, selecting from the rows where df dot suit is equal to, in quotes, a heart, making sure to use the same capitalization. Like I've capitalized the H here.
And it looks like, ooh, it looks like I didn't, so I need to make sure to not capitalize it. And it looks like we get 7,465 rows.
7,465. So we know our simulation looks good because the expected value that you gave me of 7,500 is very close to what our simulation we got in our estimated probability by using simulation.
Yes.
So that's a good sign. And the last analysis question, what's the estimated probability of drawing a queen? So Carly, if we have 30,000 cards we drew, how many of those cards would be a queen?
So let's see, that's 4 out of 52 or 1 out of 13?
So 30,000 times 1 divided by 13. So we're going to use Python to kind of help us out to do the math.
It's a decimal. It's 2,307.69.
2307?
Yeah.
0.69, though, right?
0.69, yes.
So I'm going to round it to 2308. So that's our expected value. And now we can use the data frame. This time we want to look at the column rank, and we want to make sure that rank is equal to a Q. So I would write df at df.rank is double equal to capital Q inside of quotes, because we're treating all of these suits as, all of these ranks as strings. And if we look at how many times we got a queen, how many times did df.rank is equal to Q?
df.
Oh, did you get an error?
Yes.
What error did you get?
I did. It says, the above exception was the direct cause of the following exception. Okay, hold on. Key error, false.
Do you see any other text in there? Maybe something to do with rank.
No.
So Python's being cryptic at this point.
Yeah.
But what's almost certainly happening is rank is a statistical term. So whenever you use this dot notation, this is kind of the shorthand of using the square bracket notation. So whenever I see an error like that, and I'm pretty certain of the code, the first thing I'm going to try and do is I'm going to change this line to df at rank in quotes. And this explicitly says, I want to look at the column named rank. Using the dot notation is a way that says, I want to look at the column or the function called rank, but functions have priorities over column names.
Yes, so that fixed my error, and now I see all of these queens, and there are 2,333 of them.
2,333, and we see that that's so close to 2308. Like we
Yeah.
again got that prediction that's right there, really close to expected value.
This is a really good way to check our expected values.
So this is some more increasingly complicated simulations that we're trying to simulate real things. And by adding just a little bit more code, we could think about simulating like a hand of poker or a game of, you play Euclair?
Euchre.
You play euchre?
Yeah.
Euclair, it's not a Zerd or something. Who knows?
Yeah, Euclair. But we can simulate a hand of euchre. That'd be fun.
So any card game, you can simulate now because we have
Dominion.
cards. Exactly. Not a 52 card deck, but my favorite
Yeah.
game. So that's just a bit of simulation, and we're going to keep adding in this series more and more complexity to simulation so we can really dive into solving really complicated problems through simulation.